Let's suppose that we have an ant that's crawling around on a piece of graph paper like this. How could we describe the location of the ant? Well, when the ant is at this spot, we could just write down the coordinates of its location. So this spot is 2, 2. But it doesn't stay there, right? The ant is crawling around. That's the whole idea of this setup. So, after a while, maybe the ant is crawling over to here. So then it's at 1, 5. And then over to there maybe. So now it's at -3, 3, and it keeps wandering around the plane like this. You can see that the x coordinate of its location, right? Normally we'd call it the x coordinate of its location x, but since it's moving around, the x coordinate of its location actually changes. It's actually a function of time. So we can't just call its x coordinate x. We would have to call it x of t, since it's a function of time. And the same thing goes for its y coordinate, right? Its y coordinate changes from place to place. So we can't call its y coordinate just y. We have to call it y of t. We have to use a function. So what we get is, it's a point like we're used to, but the coordinates, instead of being numbers, they're actually functions of time. This is such a common situation that there's a whole vocabulary around this kind of setup. This sort of thing, a point that moves around the plane as a function of time, is called a parametric curve. So a parametric curve, or some people call them parametric equations, is just a pair of coordinate functions, x of t and y of t. Some people like to write them like this: x equals some function and y equals some function. And we're going to insist that these functions be continuous on some interval in t. Of course, eventually we're going to do calculus with these functions, in which case they have to be differentiable, not just continuous. And our usual interpretation for this is, for this kind of setup, is that t is time, and these parametric equations describe a point that's moving around in the xy plane. As it moves around, it actually traces out a curve. Some people draw the distinction between these functions, which they call the parametric equations, and the curve that they trace out, which they call the parametric curve. For me, the distinction isn't so important. But the curve that these things trace out we'll call the graph of the parametric curve. So let's look at an example. Here's a parametric curve, right, or a set of parametric equations. It's a pair of coordinate functions, one for the x coordinate and one for the y coordinate. So let's sketch a graph of this. Since this is a point that's wandering around in the xy plane, we can just plot some points to get an idea of where this curve is at any given time. So, we'll have to pick some time values, and we'll calculate the corresponding x coordinates and the corresponding y coordinates. So this is different than a graph where y is a function of x. If y is a function of x, you only need 2 columns. But here we have 3 variables: the one input variable, the parameter t, and the 2 functions or output variables, x and y. So this particular parametric curve, its domain is all real numbers for t. So let's, start at -1 and just plot a few. So when t is -1, then t squared is 1, -3 is -2. And then when t is -1, for y we get -2, -4, so -6. So that's going to look something like this. So -2 in the x direction, and then -6 in the y direction, so here. And we've plotted this point, but notice that there's nothing on this graph that actually indicates what t value this point corresponds to. If you want to decorate the graph with t values, you can. So we could write t equals -1 right here, just as a note to ourselves that that's the t value that produced that point. Okay, let's plot a few more points. So when t is 0, x is -3, and it looks like y is going to be -4. So -3, -4, that's here. So that's when t is 0. When t is 1, we get minus 2 and minus 2. So there. And maybe we'll do one more. When t is 2, let's see, for x we get 1, and for y we get 0. So that's going to be right here. So that's when t is 2. All right. Of course, I've just chosen a few t values here. In reality, since the domain of this parametric curve is all real numbers, there are, we could fill in the gaps by plotting all the points for the t values in between the t values that I've chosen. And if we did that, then it would fill in the gaps between these points. In fact, for this particular parametric curve, it turns out that if you do fill in the gaps, it looks something like this. Okay? And as t increases, we're going that way along the graph. So the idea here is that we can get some idea of what the graph of a parametric curve looks like just by plugging in points. Of course, plugging in points is not the most efficient way to get an idea of what the graph looks like, so we'll have to come up with other tools to understand what curve a parametric curve traces out.